last lecture, we talked about how neural networks work by a simple XNOR example. I hope that was quite clear. Now, in the end, we raised a very important question, as in, how do we update the weights? How do we change the weights? So, for doing that, let's again solve a simple problem to understand what exactly do we have in mind or how we are going to approach it. So, we have already defined about the regression problem. Now, as in regression, we know that we have some set of points and we define one line that best resembles those points. So in two-dimensional, the regression is nothing but like simply a line mx plus b, or in other terms I can write as theta 1x plus theta naught as y. So this is our line, and like as linear regression we can also define, so okay, like as in linear regression, we can also define a neural network that resembles this ideology. So it's quite simple. So we have one neuron, and if we simply give x here and this is 1, so this would be theta naught, this would be theta 1, and this would be y. So if you remember the previous tutorial, so it is theta naught times 1, that is theta naught, plus theta 1 times x, that is theta 1x. So this neural network itself would do the job of linear regression. Now the question is, how do we update these weights? So of course you will be given some set of points. Let's say x is equals to 2, and for this case the y is actually 4. Let's say x, another point could be 3, y is let's say 6. Other point could be, I don't know, maybe 4, y is 8, or something like that. Some set of points you are given, and you need to design a neural network that defines a line which simply does y is equals to fx, where fx is simply this function, right? Now the question is, how do we define the best theta so that it does a quite good job of doing this linear regression? Well, in order to do that, first of all we need to also understand that, okay, if we find some theta naught and theta 1, we do this function, so we get some value y. How do I know that how much good or bad this y is? Well, we simply compare this y to the original y and simply find out sort of a difference that tells us, okay, this is how good or bad it is. So if I define it as like y cap, which simply represent the prediction, so this is simply the output of this function. So the actual or loss we can define is that my true answer for this particular set of points, let's say in this case this is the first part, so this is, let's say, y minus y cap, right? So if y is, let's say, 4, and suppose we took some set of points for theta naught and theta 1, I selected randomly and I got this output as, let's say, 2.5. so what should be the answer? Then 1.5 is actually our loss. So we can define some sort of loss in here, and that loss I defined is, let's say, y minus y cap, and right now I'm just squaring it because let's say I want all the things to be positive. What if y cap is higher than y, then it would be negative. So you can either do this, or maybe other terms, y minus y cap, you can also take absolute value. Well, absolute value is what? Well, it simply gives the positive sign. So if it is negative x, so if it is normal x, then it's x, negative x, then also it is x. But right now we will simply go with this. Let's define a loss as simply this function. Now let's talk about how do we take these theta naught so that it gets good prediction, or in other terms, if your y is actually very close to y cap, then also you will get small loss, and small loss basically means that y cap is more closer to y, and y cap is more closer to y means your output is more closer to your actual answer, and that means that good prediction, right? So let's understand something. If we this loss is y minus y cap square, or you can also write this as theta naught plus theta 1 x. That is simply your prediction, right? So if you plot this, let's just plot this loss function. Why we are plotting it? Because it will give you some good intuition. Well, it's simply a quadratic function, as you can see. And how does a quadratic function looks like? Well, it would look like something like this, like a parabola. Now of course you can plot it, like taking some set of points for some values of x and then some random values of theta naught, theta 1, and then you get the pairs of x comma y. But if you keep on doing it, you will simply get some sort of this quadratic function. It might be little bit wider, little bit narrower, depending on what set of points you take, but in general it will looks like a parabola because it's a quadratic function. Now if I draw, so this is your y cap, right? This is actually the y cap, the output. Now if you take different values of theta naught and theta 1, so for one particular x you will get different points on this curve, right? So that means this here is actually theta. Now if we look at this particular curve, if at this particular point we would have some value of y cap, at this particular point we would have some value of another y cap, like at this particular theta we would have another y cap. Which point do you think that we should take so that it actually gives a minimum loss? Well, if you simply see, it's actually this point. So if we take the minimum of this particular curve, so this would actually give us minimum loss, right? It will actually give us minimum loss. So I could say this minima, so local minima, or in this case you can also say global minima. So global minima would actually give you minimum loss. Okay, so now I know that if somehow we can define the minima of a loss, then we can actually simply take those theta for this particular minimum loss, and then we simply put it at this particular function. If we simply put it at this function, then you will get minimum loss, and minimum loss means your actual answer is very close to predicted answer, and that means you have done a quite good job. That means you have defined a good neural network that actually does this linear regression. Now right now we just take one x, right? Like I said here, if you fix one particular x, then you get theta naught, and you take different values of theta naught and theta 1, and you get this particular curve. But ideally, like I said here, there are several different points. So the loss function would simply, if we can take average, so if n number of points are there, we can simply take average for every point. So y minus theta naught plus theta 1 xi. So this is your actual loss, right? So we simply find out loss for every single point, and we simply take the average. So if you plot this loss function, you will get quadratic. And if we take theta, like if we take a local minima, if we find the local minima of this loss function, then you actually get good theta. Now you might be wondering here that I just took one x, now we have several x's. So how can is it possible that if we take one theta and make it loss completely zero? Well, completely zero would be cases like, suppose if the points would exactly like this and one line can exactly fit it. So just for this theta, you can actually get a good loss, that is actually zero loss. But what if points are like this? Well, in this case you will get a line like those theta that actually are very close to these points, and that is also a good answer. So now we know that how local minima and global minima can help us. Now how do we find it? Well, it's quite simple. How do I know that it's simple? If we somehow find out that how this loss function is changing, if we change this theta, let's say at this particular point I have some value of y cap. Okay, now if I take, let's say if I add one theta, a very small value of theta in here, now I see that I get another loss function here, which is actually smaller than this particular y cap, right? So I know that, okay, if I keep on moving in this direction, then I will somehow end up at minima, right? Similarly, if I take another point here, and instead of uh, let's say going down, if I go up, right, if I simply go up, then I know that I'm actually increasing the loss, so I shouldn't go up, I should actually go down, right? Now, how do we define this going up or going down? Well, it's quite simple. If at this particular point, let's say at this point we have some value theta naught, right? So theta naught. Now if I add some value, let's say if I add some value, let's say 2, let's say if I add a value 2, that means now if this is theta naught, then this would be theta naught plus 2, right? And let's say this is theta naught plus 4. So that basically means at this particular point, increasing, like adding some value would actually give us a will actually move towards minima, right? So if I let's say subtract theta naught minus 2, that means if this is theta naught, so theta naught minus 2 would be something here, that means a higher loss. That means I shouldn't do minus, I actually should go plus. That means I should actually add. So this adding small values to a particular point and actually changing and actually knowing that whether my y cap sort of increases or decreases, this is what called as gradient. So it is defined as del L over del theta, that is simply differentiating over theta. So this differentiation actually simply tells you that if we make a small change in theta, does your loss function increase or decrease? Now if it is greater than 0, if this del L over del theta comes out to be greater than 0, sorry, that means that increasing theta will actually increase the loss function. And if it turns out to be less than 0, then increasing theta will actually decrease the loss function. And if it is actually 0, then that means increasing or decreasing theta does not have any effect on the loss function. So that means if I can simply so our loss function is, let's say just take for 1 point, okay, if let's say n is 1, so if n is 1, then it would be simply y minus theta naught plus theta 1 x1 square. So if I simply find del L over del theta, how do I find? Because there are two thetas here. Well, you can do partial differentiation. Partial differentiation in very simple terms is nothing but differentiate loss function with first theta naught, differentiate loss function with theta 1, and then simply put their values in here, and that would basically be your del L over del theta, right? Well, I'm not gonna do that. It would be very quite nerdy, but okay, let's do it for one value. Let's say if it is del L over del theta naught, then what would it would be? Well, it would be 2 times y minus theta naught plus theta 1 x1 times theta naught. So times del over del theta naught, it would be theta naught plus theta 1 x1. That would be minus in here and plus y. It's just the chain rule. Now if you differentiate it, this is 1, this would be 0, this would be 0. So that means this entire term would actually go to 1. So you simply put the value of y, you simply take whatever your theta naught and theta 1 actually are right now, put it x1 and you get the gradient. Now I know that whether the gradient is with the sign, I know that whether the loss would increase or decrease, so I just move in the opposite direction of it. By default, the gradient actually points to the direction where the function is increasing, so I will always move in the negative direction of the gradient so that the function sort of decreases. So that's how we actually update the parameter. So the summary for this lecture is quite simple, that we first of all define the loss function. Now once we define the loss function, we simply differentiate with respect to the theta, that is the parameters, and after you got those gradient, we simply move in the negative direction of the gradient to get other points. How do I move in the negative direction? Well, if I just take theta naught, so theta naught, let's say I found the gradient, so it would be theta naught, so I will move in the negative direction of the gradient, and let's say I take some constant eta or whatever times del L over del theta naught. Now this eta means, let's say if eta is 0.2, then simply I will move 0.2 times the gradient. That means it would be theta naught is equals to, sorry, theta naught minus 0.2 times, let's say if the gradient is 1, then I will simply subtract 0.2. So this would be my new theta naught. Similarly, I can do for theta 1. Now when you have theta naught and theta 1, now you know the new value of theta naught and theta 1. You can again now put it in this expression, get the new y, then again calculate the loss function, then again calculate the gradient, and so on. And we keep on doing it unless we reach a very small value of loss function, and that means our neural network is now doing a good job. So I guess that's it for today. In the next lecture, we'll talk about how this actually happens in neural network. I mean, do we have to do this manually, this all calculation and everything? Well, the answer is no. That's why the framework TensorFlow and other frameworks out there like PyTorch actually helps us a lot, because this because they actually does this automatically in the back, and we don't have to worry about it at all. So in the next lecture, I'll give you a very small example as in how actually this happens in neural network, which called the technique that is they use is what called as the backpropagation. And I will explain this by a very simple example, that as in how they take the gradient and update the weights so that we don't have to do this manual job all the time. Until next time, Radhe Radhe.